Let's move on to cohort studies. These are studies that identify a group of healthy people, the cohort, and follow them over time for the development of disease. Typically, we classify the cohort, the individuals in the cohort, based upon some exposure, and it's critical that we make sure that the unexposed group of participants is similar to the exposed group in all variables with the exception of the exposure. In a cohort design, we're able to measure the occurrence or the incidence of the health outcome in the exposed and the unexposed population. The analysis of cohort studies allows us to compare the occurrence of the health event of interest across these exposure categories, and the estimate of the association is the relative risk. That is, the risk of the disease among the exposed compared to the risk of disease among the unexposed. Cohort studies can further be categorized as prospective or retrospective. Prospective designs, or concurrent designs, are assembled at the present time and longitudinally followed forward in time. The advantage to a prospective cohort is the ability to design and conduct the study specifically to achieve your aims. The data collection, the exposure assessment, the quality control, everything that you've done in your protocol is specifically tailored to your hypothesis. Of course, the disadvantage to this design is the time that it is required to design, enroll, and most importantly, follow the cohort until the onset of the health outcome that you're interested in. And that results typically in rather expensive studies. Cohort studies may also be retrospective or historical. These are cohort studies that have identified a cohort of individuals that has been assembled in the past and followed to the present time. These designs are often used in occupational epidemiology, where you might be able to link, for example, occupational records to existing health or mortality data. You still get the advantage of conducting a longitudinal study of a cohort that was without disease at its start, but because it's a retrospective design, it's less time to the completion of the study because the data already exists, and therefore it's typically less expensive. The drawback to this design, of course, is that it's dependent upon data that may or may not have been collected and stored. So here's a diagram of a prospective cohort study. As you can see, in this design, you're going to start in the present, select your cohort from the overall population, and the individuals enrolled in the cohort are classified as exposed and unexposed. These individuals are then followed longitudinally to assess the development of the disease. The incidence of the disease in the exposed and the unexposed populations is ascertained, and the ratio of the two is the estimate of the relative risk. The diagram of a retrospective cohort is very similar, but the difference is that the cohort was established in the past, and the incidence of disease among the exposed and the unexposed populations was ascertained between the past and the present, including the present. In this case, the investigator uses previously collected data to identify the study population, the exposure status, and the disease incidence, keeping in mind that the disease may also be assessed at the present time. A major advantage to the cohort design is the ability to estimate the relative risk. That is, the risk of disease among the exposed compared to the risk among the unexposed. In our simple 2x2 example, the risk of disease among the exposed is A over A plus B, while the risk of disease among the unexposed is C over C plus D. The ratio of the two is the relative risk for a disease given exposure. Cohort studies also enable survival analyses to be conducted comparing the time to outcome between the exposed and the unexposed groups. These analyses are frequently conducted using life tables and Kaplan-Meier methods. Under the Kaplan-Meier approach, the probability of each event at the time it occurs is calculated, and the conditional probability Q sub I is calculated as the number of events at time I divided by the number of study participants still under observation at time I. Let's walk through an example of a calculation of a Kaplan-Meier curve. So the figure on this slide on the left depicts a hypothetical cohort of 10 individuals that have been followed for 24 months. At each month, 3 possible outcomes are observed. Either the individual remains in the cohort without the health event, the individual is lost to follow-up, here indicated with a C representing censored values, or the health event has occurred and has been observed. In this case, the health event is death. At the time of each event, in this figure, at times 1, 3, 9, 13, 17, and 20 months, the conditional probability of the event is calculated as the number of individuals having the event divided by the number of individuals remaining at risk, that is, the number of individuals that are still under observation at that time. The conditional probability of survival then is calculated as 1 minus the conditional probability of the event, and the cumulative probability of survival at each time point is the product of the conditional probabilities of survival up to that time point. So in this case, the first event was observed at month number 1. The number of individuals that were in the cohort at risk were 10. The number of events was 1. The conditional probability of the event then was 1 divided by 10, or 0.1, and the conditional probability of survival then is 1 minus 0.1, or 0.9. Because this is the first time point, the cumulative probability of survival at this time was 0.9. So let's move now to 9 months of follow-up. We see at that time point there are 7 individuals that remain in the study under observation. So individuals 10 and 1 have died, and the individual 7 was lost to follow-up. We observe another death at month 9, so the conditional probability of the event was 1 over 7, or 0.143. The conditional probability then is 1 minus 0.143, or 0.857. And the cumulative probability of survival is the product of the conditional probabilities of survival up to this point, or 0.9 times 0.875 times 0.857, which equals 0.675. So a Kaplan-Meier curve is then a graphical representation of the cumulative probabilities of survival at each time point. So you can see then on the curve on the right side of this slide, the cumulative probabilities of survival are plotted on the y-axis and the follow-up time is presented on the x-axis. So let's go through an example of a cohort study, and I'm going to give you an example of the study that I'm involved with, the Cincinnati Childhood Allergy and Air Pollution Study. So the hypothesis of this study is that early childhood exposure to air pollution, and specifically diesel exhaust particles, is significantly associated with the development of allergic disease and asthma in childhood. So the study consisted of full-term infants that were born in the Ohio-Kentucky River Valley region, and these were identified from birth records in 2001 to 2003. And again, in the classic cohort study design, we identified what we thought were an exposed population and an unexposed population. Those that were defined as exposed were the infants residing less than 400 meters from a major road, and the unexposed population were infants that were residing greater than 1,500 meters from a major road. And so we're going to prospectively follow them, looking for the development of allergies and asthma. Just to give you an idea of the time and expense it takes to do a prospective cohort study, the recruitment took almost 3 years. We contacted more than 7,000 individuals and families. 2,265 of them actually responded to our eligibility survey. Of those, 1,879 were eligible for the study. We had 1,152 parents come into one of the clinics and actually do a skin prick test. We had 881 parents that were positive, and so therefore were eligible to be enrolled. And in the end, we had 762 infants enrolled in the study, meaning that they completed at least one study visit prior to the age of 3. So we started with more than 7,000 points of contact to end up with 762 infants eventually enrolled into the study. And so we've been following this cohort now for more than 12 years. But this is some data, real data now, showing you the relative risk for developing asthma at age 7. And so if you look at the 2x2 table here, we had 140 children who remained in the study at age 7 that were exposed to air pollution at birth. Of those 140, 30 have asthma and 110 did not. We had 458 kids who were not exposed to air pollution at birth remaining in the study at age 7. Of those 458 kids, 65 of them had asthma at age 7, 393 did not. And so if we calculate the incidence of disease among the exposed population, that would be 30 out of the 140, or 0.21. The incidence rate of disease among the children who are not exposed to air pollution at birth is 65 out of 458, or 0.14. And so the relative risk for developing asthma at age 7, the ratio of the two, 0.21 over 0.14, and that's 1.5. So a 50% increased risk in developing asthma among those children who were exposed to air pollution at birth. Here's a Kaplan-Meier curve presenting the cumulative probabilities of survival. So in this case, it's the time to asthma diagnosis for the CAPS cohort. The blue curve represents the cumulative probabilities of survival. And remember, in this case, survival is not having been diagnosed with asthma. And the cumulative probabilities of survival on the blue curve are those children in the cohort who were exposed to low levels of air pollution at birth. The red curve is the cumulative probabilities of survival among children who were exposed to high levels of air pollution at birth. So what you can see from this figure is not only are the children who are exposed to high levels of air pollution more likely to develop asthma, but the time to asthma onset is shorter among those children with high levels of air pollution exposure at birth. There are a number of important things to consider when you're doing a cohort study. First, the information you collect from your study participants has to be collected in the same way between the exposed and the unexposed groups. If this is not done properly, you run the risk of introducing bias into your study. It's also important to blind the investigators to the extent possible regarding both the exposure and the disease status of the participants. You'll also want to be sure to standardize the outcome measures and definitions across the study. The other thing to keep in mind with cohorts is the critical importance of retention. This is absolutely essential to the success of your cohort study. If you lose participants to follow up at different rates among the exposed and the unexposed groups, you risk introducing bias into your study. This is also true among withdrawals, so maintaining regular contact with study participants is essential. In the CAP study, we collect information regularly and we consistently find reasons to contact participants so we can update our records. Study mailings, outings, events at the Cincinnati Zoo, Cincinnati Reds games, study updates, emails, websites, internet searches. We use multiple approaches to making sure that we contact and keep track of our participants, constantly updating their addresses, their email addresses, and their phone numbers. So let's wrap up our discussion of cohort studies by summarizing the advantages and disadvantages of the design. On the strength side, cohort studies provide direct information on the sequence of events leading from exposure to disease, and this is essential to claiming causality. Cohort studies also might facilitate multiple outcomes and exposures to be studied. So for example, in the CAPS cohort, we are now examining neurodevelopment in the cohort in addition to allergies and asthma in order to study the association between early air pollution exposure and brain development. That is, because we've assessed early exposure to air pollution and we have a cohort of children without disease, we're able to follow them prospectively not only for allergies and asthma as the study was originally designed, but also now for neurodevelopmental outcomes during adolescence. Some of the disadvantages of cohort design is of course the expense and the time required. Cohort studies are also not suitable for diseases with long latency since you're going to need to follow the participants until they develop the disease, and you're just not able to do that for diseases that develop over the course of 20 or 30 years. Cohorts are also not suitable to study rare diseases because the sample sizes that would be required would just simply be too large to be able to feasibly do this type of study. There's also the potential for exposures in cohort studies to change over time because of natural changes. So for example, people moving addresses, therefore resulting in changing air pollution exposures, for example, or by altering habits or diets simply because they recognize that they're part of a study and they're more aware, so they make lifestyle changes.